All right, in today's lecture, we're going to start our Chapter 5 material on sequences and series. And in section 5.1, we'll start by introducing sequences. In particular, in our course, we're going to be working with infinite sequences. So let's start by defining what is a sequence. A sequence is defined to be any ordered list of numbers. So an infinite sequence would be an infinite list of numbers. So numbers A1, A2, A3, A4, and so on out to infinity. Now, if we want to reference a specific term, we might use the notation A sub n, and the subscript that we're using here, n, is what is called the index variable of our sequence. And the number A sub n itself is called the nth term of that sequence. So these different numbers are the terms of our sequence, and the one that has a subscript of n is called the nth term. So A1 is the first term, A2 is the second term, A3 is the third term, and so on. Now, the notation that we typically use for infinite sequences would be either to write the expression for the nth term, A sub n, written in curly braces, or if we need to be a little more specific, we would write A sub n in curly braces with the subscript n equals 1 in the superscript infinity if we want to denote a little more specifically that the first term of our sequence will correspond to n equals 1. So to get more familiar with infinite sequences, let's look at this first example where we are given the general term of a sequence and we are asked to write out the first 5 terms. So in this first part, part A, we have 2n over n plus 1 from n equals 1 to infinity. So this expression that we have in curly braces is the expression for the nth term. And in this example, the first term of our sequence will correspond to n equals 1. So to get the first term of our sequence, we will plug in 1 for n, and let's see what we have. We have 2 divided by 2, or 1, for the first term of our sequence. If we plug in 2 for n, we would get the second term in our sequence, which would be 4 over 3. To get the third term in our sequence, we plug in 3, and we would have 6 over 4, or 3 halves. To get the fourth term, we would plug in 4 for n, which would give us 8 fifths. To get the next term, our fifth term, we would plug in 5 for n, which would give us 10 over 6, and then we could keep listing terms. So these values that we're getting, these terms in our sequence, would correspond to the values n equals 1, n equals 2, n equals 3, and so on. So the first 5 terms of our sequence are written here. We can either simplify these terms or just write them out in their unsimplified form. So in part B, we have the sequence defined by n minus 2 divided by n plus 2, starting at n equals 1 and going to infinity. So to get the first term in this sequence, we will plug in n equals 1, which would give us negative 1 over 3. To get the second term, we would plug in n equals 2, which would give us 0 over 4, or simply 0. To get the third term, we would plug in n equals 3, and that would give us 1 over 5. To get our fourth term, we plug in n equals 4, which would give us 2 over 6, or 1/3 if we prefer. And to get our fifth term, we plug in 5 for n, which would give us 3 over 7. And we could keep listing these terms. So here, we wrote out the first 5 terms of our sequence, and we could keep listing these to get as many terms as we needed. Now, in general, to get a specific term for a sequence, well, we don't have to list out all the terms to get there. For instance, in part B, we could ask the question, what is the 100th term of our sequence? And to get the 100th term, well, we're looking for a sub 100, which means that we would plug 100 in for n. So we would have 98 over 102 for that 100th term. So we don't have to list the first 99 terms to get the 100th one. We can just plug in whatever value of n we're interested in to find any term for our sequence along the way. All right. Now, in this next example, we'll see a problem that is a little more practical. This is working in the opposite direction of the problem that we just started with, but these problems are a little bit more practical. We'll see throughout Chapter 5. And so here we are given the first several terms of a sequence, and we're asked to find a formula for the general term a sub n of that sequence. So in this first example, part A, the first several terms of our sequence are 1/2, 1/4, 1/8, 1/16, 1 over 32, and so on. So we see that each term of our sequence is a fraction of the form 1 over some number, and it looks like all of the numbers in our denominator are powers of 2. 2, 4, 8, 16, 32, and so on. So in general, the nth term of this sequence would have the form of a fraction 1 over 2 raised to the nth power, where in this example, we would have n starting at 1, so that our first term would correspond to our 1/2. So here a sub n would be 1 over 2 to the n, or if we want to write this in a different way, we could say 1 over 2 to the n, where n goes from 1 to infinity. So this would be the formula for our nth term. So let's look at some other ones. In part B, we have the first several terms of our sequence are positive 1/4, negative 2/9, positive 3/16, negative 4/25, 5 over 36, and so on. So here our terms of the sequence are a little bit more complicated. So let's see if we can find a general term or the formula for the general term a sub n. So in this example, again, our terms all involve fractions. And usually when the general terms of my sequence involve fractions, I like to think about the pattern in the numerator and the denominator separately. So if I look at the numerator of these different terms for the sequence, they are 1, 2, 3, 4, and 5. So in general, the nth term will have a numerator of n, where we're starting with n equals to 1, and then moving to 2, 3, 4, 5, and so on. Now, if we look at the denominator for each of these terms, we have 4, 9, 16, 25, and 36, which we recognize are all squares of different integer values. That denominator for my first term is 2 squared. For the second term, 3 squared. The next term, 4 squared, 5 squared, and 6 squared. So in general, we see here that the number that we're squaring for the denominator is always 1 greater than the term in our numerator. And the last thing that we notice for the pattern in the terms of this sequence is that they're alternating in sign. The first one's positive, second one's negative, then positive, negative, positive, and so on. So to capture an alternating sign, we could think about multiplying this number by -1 to some power. Now, the power that I raise -1 to, if we're going to have an alternating sign, we could either take it to the n power or the n plus 1 power. And in this example, I know that when n is equal to 1, when I'm looking at this first term, I want to have a positive number. So in this example, I'm going to take -1 to the n plus 1 power. So if n is odd, that is for my first term, my third term, my fifth term, and so on, I'm going to have an even power of -1 so that each of those terms is a positive. So in this example, our general term for the sequence would be the following. So let's look at another one. In part C, we have 1, 1/2, 1 over 6, 1 over 24, 1 over 120, and so on. So there's a few ways that we could think about describing this general pattern. Here, our first term is 1, and we could maybe think about that first term as being a fraction, 1 divided by itself. Now, the next term in our sequence is 1/2. So we have the same numerator, 1, it looks like, for all the terms in our sequence, and just our denominator is changing. So here we had 1 over 2. Now for the next term in our sequence, we had 1 over 6, and I could think about our denominator 6 as being 2 times 3. And then the next term in our sequence, 1 over 24, well, 1 over 24 could be thought of as 1 over 2 times 3 times 4. And then for my fifth term, we had 1 over 120. Now, 120 can be factored as the product of 2 times 3 times 4 times 5, and so on. So here, it looks like the general pattern that appears in our denominator is that we're multiplying the next term, to get the next term in our sequence, we're multiplying the previous one by the next highest integer. To go from 1 to 1/2, we multiplied our denominator by 2. To go from 1/2 to 1/6, we multiplied the denominator by 3. To go from 1/6 to 1 over 24, we multiplied by 4. And to go from 1 over 24 to 1 over 120, we multiply that denominator by 5. So in general, this pattern, A sub n, or the general term for this pattern, could be described as 1 over n factorial. Now remember, the notation n factorial is used to denote the product of n times n minus 1 times n minus 2 and the product of all the subsequent integers until we get down to 3 times 2 times 1. So as an example, 4 factorial would be 4 times 3 times 2 times 1, or 24. So in general, the nth term of that sequence would be 1 over n factorial. So let's look at some other ones. In part D, we have the sequence 0, 2, 0, 2, 0, 2, and so on. So there's a few ways that we could think about describing the general term of this sequence. So it's pretty clear that our terms are just going to alternate between 0 and 2. So one way that we could describe this sequence would be as a piecewise function. A sub n, that is the nth term of my sequence, would be equal to 0 if n is odd. That is, the first term, the third term, the fifth term, and so on would all be 0, and an is equal to 2 if n is even. All of the even terms of my sequence are 2. So this would be one way to describe that. Another way, which we might describe the nth term of our sequence, is by thinking about how far these terms in our sequence are based from some central point. So 0, 2, 0, 2, 0, 2, we could think of as being 1 unit to the left or 1 unit to the right of the number 1. So another way to describe this would be by taking 1 plus -1 to the nth power. So that if n is an odd number, -1 to the nth is -1, and we get 0. And if n is an even number, -1 to the n would give us a +1, and we would have 2. Now, there are several other ways which we could describe the terms of this sequence. These are probably the easiest ones. So here we might choose this one, which would be a little bit easier because we don't have to think about it as being defined piecewise. So let's look at the problem of interest that we'll be considering throughout most of Chapter 5. Now, if in this first example, we could ask ourselves, okay, if we were to keep listing terms of this sequence, what's happening with the subsequent terms? Is there any number which they seem to be approaching? So in this example, we had 1/2, 1/4, 1/8, 1/16, and so on. So it seems like as we keep listing terms, they're getting smaller and smaller. So here, the terms of our sequence, a sub n, seem to be approaching 0 as n gets larger. Now for our second example, we had these terms that were alternating in sign, but the values of our fraction were getting smaller and smaller. So here we would have, again, a sub n seems to be approaching 0 as n gets larger. For this next term, 1, 1/2, 1/6, 1/24, 1 over 120, we see again that the terms of my sequence seem to be getting smaller, approaching 0 as we keep listing them. For this Part D example, as n gets larger, our terms are going to keep oscillating between 0 and 2. There is no number that a sub n seems to approach. So the question that we're interested in for infinite sequences is determining their convergence or divergence. So let's introduce some terminology here. We would say if the limiting value of a sub n as n approaches infinity is equal to L, then the sequence A sub n converges to the value of L. Otherwise, we would say that our sequence A sub n diverges. So I could think about plotting the terms of my sequence on a set of axes. So say if our horizontal axis is n, and my vertical axis would be A sub n, the nth term, well, we would start with n equals to 1 and find our first term, then take n equals 2 to get our second term, n equals 3, n equals 4, n equals 5, and so on. And if we look at the terms of this sequence, as n is getting larger, it seems like they're closing in on this constant value, capital L. So if the limit of that nth term is equal to L, we would say that that sequence is converging to L. Now, another example of the type of convergence we might see if we are listing our terms for n equals 1, 2, 3, and so on would be the following. We might have some sequence whose terms are oscillating back and forth across some constant value L, and if we keep listing the terms of our sequence, it seems like they're getting closer and closer to this limiting value of L. So in this case, we would say those sequences are converging to the value L. So a problem of interest throughout this chapter will be to determine whether a given sequence converges or diverges. And to address that, we're going to take the limiting value of our expression for the nth term, a sub n, as n approaches infinity, and see if that limit exists. So in our first example, we are given the general term of our sequence is 4n minus 3 over 3n plus 4. And we're going to be interested in the limit of this expression as n gets infinitely large. So here, there's a couple of ways we could go about evaluating our limit. One way would be to recall what you saw in your Calculus 1 class. If we are taking the infinite limit of a rational function, that is a quotient of two polynomials, we would look at which term, our numerator or denominator, has the largest power of n. And in this case, we see that both the numerator and denominator involve n to the first for the highest power of n. So in the case that your numerator and denominator have the same highest power on top and bottom, then you would look at the ratio of the coefficients for that highest power on top and bottom, and that ratio is your limit. So in this case, we would have a limit of 4/3. Now, another way that we could maybe think about evaluating this limit would be by considering L'Hopital's rule. If n is becoming infinitely large, then both our numerator and denominator are approaching infinity. We have an indeterminate form or indeterminate limit of the form infinity over infinity. So if we were to apply L'Hopital's rule, that says we would look at the limit of the ratio of the derivatives of the numerator and denominator. So differentiating the numerator, we would have 4, and differentiating our denominator, we have 3. And now the limit of a constant 4/3 would be 4/3. So in this second case, we were applying L'Hopital's rule. But regardless of how we evaluate this limit, we get a limiting value of 4/3. And the terminology that we would use for this infinite sequence is that the sequence converges to 4/3. So let's look at some other ones. In this first one, we had a relatively simple limit to evaluate. So in this next one, part B, we have a sub n is the square root of a rational function. And we're interested in whether this sequence would converge or diverge. So here, we're going to be looking at the limit as n approaches infinity of the square root of 2n squared plus 3 divided by 18n squared minus 6. Now, I know that the square root function is a continuous function, so I could move my limit inside of the square root here. And I would have the square root of the limit as n approaches infinity of 2n squared plus 3 divided by 18n squared minus 6. So now, underneath the square root, we have the infinite limit of a rational function. And now this is pretty similar to what we saw in part A. If we look at the numerator and denominator, we see that they involve n squared as the highest power of n. So the same highest power for n on top and bottom. So the limiting value as n approaches infinity would be given by the ratio of those coefficients for the highest powers of n. In this case, 2/18. So we would have the square root of 2/18, which would be the square root of 1/9 or 1/3 for our limit. So here we would say that our sequence converges to the value 1/3. So let's look at some other ones. In part C, we have the general term of our sequence is n divided by the natural log of n. And to determine convergence or divergence, we're going to look at the values of that nth term as n becomes large. And we see here, if we were to take the limit of the numerator and denominator separately, both the numerator and denominator become infinitely large. So as we saw in that first example, we have an indeterminate limit of the form infinity over infinity, which means that we could apply L'Hopital's rule. Now, to use L'Hopital's rule, we're supposed to take the same limit, that is the limit as n approaches infinity, and we look at the derivative of our numerator and denominator. So here the derivative of the numerator is 1, and we're dividing by the derivative of natural log of n, which is 1/n. Now, if we simplify, 1 divided by 1/n is n. So the limit of n as n approaches infinity is undefined. Our limit does not exist. The value of n becomes unboundedly large. So if our limiting value is not some real number, we say the sequence diverges. And in this case, we can say it diverges to positive infinity. In general, we would say it diverges, and if possible, we would say what it seems to be diverging towards. So let's look at some other ones. Get a lot of practice with determining convergence or divergence. So in part D, we have a sub n is natural log 4n plus 1 minus the natural log of 2n plus 3. And we're going to take the limiting value of this nth term as n approaches infinity. So here, the limit of the difference in these logarithms. So here, if we were to evaluate the limit of each logarithm individually, well, both the first and second term, or both of these logarithms, diverge towards infinity. So we get something of the form infinity minus infinity, which is, again, an indeterminate form for our limits. So we need to rewrite the general term for a sub n in order to evaluate this limit. And we notice that this general term involves the difference of two logarithms involving the same base. They're both the natural logarithm. So we recall that we can rewrite the difference of two logarithms that have the same base as the log of the quotient of those terms. That is log of 4n plus 1 divided by 2n plus 3. And I know since the natural logarithm is a continuous function, we could take the limit inside of that logarithm. So I've got the natural log of, the limit as n approaches infinity, of 4n plus 1 over 2n plus 3. And now inside of the logarithm, we've got the infinite limit of a rational function. So as with our earlier examples, if we look at the highest power of n that appears in the numerator and denominator, well, both terms involve n to the first, which is the same highest power, so our limit is going to be the ratio of the coefficients for those two terms. And in this case, 4 over 2. So we have the natural log of 4 over 2, which is 2. So for this sequence, we would say that it converges to the value natural log of 2. So we may have to initially rewrite the general term of our sequence in a form that allows us to find its limit. So let's look at some other ones. In part E, we have a sub n is sine of n divided by n squared. And to determine convergence or divergence, we're going to look at the limit of this nth term as n becomes large. Now, intuitively, we might find this limit right away. We know that our numerator, sine of n, is oscillating between positive or negative 1, and my denominator, n squared, keeps getting larger and larger as n approaches infinity. So the ratio should be getting smaller, approaching 0. So intuitively, we might expect this limiting value to be 0, but how could we show that this limiting value is indeed 0? Making use of our intuition. So we probably haven't seen this type of limit in a while, but it makes use of something known as the squeeze theorem or the sandwich theorem. And I know that sine of n lies between negative 1 and positive 1 for every value of n. So since the value of sine n lies between positive and negative 1, if I were to take sine n and divide through by n squared, well, it would be greater than or equal to negative 1 over n squared and less than or equal to positive 1 over n squared. Now, what I'm trying to do is take the limit of this general term, sine of n over n squared, as n becomes large. So looking at the inequality that I had, if I were to take the limit as n approaches infinity all the way through that inequality, we would have the following. So thinking about our limit on this left-hand side, as n becomes large, -1 over n squared is approaching 0, which is less than or equal to the limit as n approaches infinity of sine n over n squared, which would be less than or equal to the limit that we had on this right-hand side. Now, for 1 over n squared, as n becomes larger and larger, our values are approaching 0. So this limit that I have in the middle is both greater than or equal to 0 and less than or equal to 0. And the only way that that's possible is if this limiting value in the middle of that inequality is also equal to 0. This follows by a result known as the squeeze theorem, or sometimes called the sandwich theorem. We find that the limit that we're interested in of sine n over n squared is 0. So we say then that this sequence converges to 0. All right. So a little bit tricky here to show that that limit is indeed equal to 0 formally. We need to make use of this squeeze theorem. Or if this were just, say, a problem in web work, if we didn't need to maybe show all of our work, we could use that intuitive approach to say that our limiting value would be 0 from the beginning. So let's look at some other ones. In part F, we have 1, 0, 1, 0, 1, 0. So we see that our terms are alternating between 1 and 0. And here, the nth term of our sequence, we could either write piecewise as 1 if n is odd, and 0 if n is even. Or we could use that same sort of approach that we had seen in our earlier example, where the numbers that are alternating in our sequence are oscillating around some central number. So here between 1 and 0, maybe 1/2, plus negative 1 to the nth power over 2. So we're taking 1/2 plus or minus 1/2. So we could take negative 1 to the n over 2. And let's see, in this case, we want our power of negative 1 to be n plus 1, so that if n is an odd number, we would have negative 1 to an even power, which would give us 1/2 plus 1/2, or 1 for all the odd terms. Now, to determine convergence or divergence, we're supposed to look at the limit of this general term as n approaches infinity. In this case, the limit of 1/2 plus negative 1 to the n plus 1 over 2. And we see, because of this alternating term, negative 1 to the n plus 1, our limit does not exist. There is no single number that the terms of our sequence are getting any closer to. They're oscillating between -1 or between 1 and 0 for all values of n. So here our limit does not exist. So if we do not have a real number for our limit, we say that the sequence diverges. And in this case, the type of divergence that we see is called divergence by oscillation. If our terms are constantly oscillating between two or maybe more than two fixed numbers, and they're not approaching any one value, we would say that our sequence diverges by oscillation. All right, so let's look at another one. In part G, we have the nth term of our sequence is defined as the nth root of n. So if we were to write out the terms of this sequence, we would have the first root of 1, the square root of 2, the third root of 3, the fourth root of 4, and so on. And we want to know, are the terms of this sequence converging to a number or not? So to answer that, we're supposed to look at the limiting value as n approaches infinity of this a sub n term. That is the nth root of n, which could be rewritten as n raised to the 1 over n power. So if we look at the limit of the base of our exponent here, n, we see, becomes infinitely large as n approaches infinity, and our exponent, 1 over n, is approaching 0 as n approaches infinity. So this is another one of those indeterminate forms. So normally, if we were to have a power function where our base is getting larger and larger, let's say infinity raised to any number, we would define that value to be infinite. And if we had any exponent whose base was a fixed number and we raised it to the 0 power, say like 1 to the 0, 2 to the 0, e to the 0, we would define that value to be 1. So in this case, for infinity to the 0 power, well, we get an indeterminate form. We're not sure what our limiting value would be. And we're going to need to make use of L'Hopital's rule. But recall, L'Hopital's rule only works in the case that we have an indeterminate form of 0 over 0 or infinity over infinity. So we'll need to manipulate this a little bit. And if we think back to Calculus 1, the way that we handle this type of indeterminate form is by making use of a logarithm. So what I'm going to do here is let my limiting value for n to the 1 over n power as n approaches infinity equal some value of L. And if I were to take the natural log of L, well, I would have the natural log of the limit as n approaches infinity of n to the 1 over n power, or because the natural logarithm is a continuous function, I can take the limit out in front of my logarithm. So I have the limit as n approaches infinity of log n to the 1 over n. Now I know for logarithmic functions, if I have the log of something raised to a power, I can bring that power out in front of my logarithm. So what I have here is the limit as n approaches infinity of 1 over n times the natural log of n, or if we prefer, as a fraction, the natural log of n divided by n. Now here, if we were to take the limit of our numerator and denominator individually, well, the natural log of n gets infinitely large as n gets large, and our denominator n also approaches infinity. So here we have an indeterminate form, or an indeterminate limit of the form infinity over infinity. So at this stage, I can apply L'Hopital's rule, which says we're going to take the limit as n approaches infinity of the quotient of the derivatives. So if I differentiate the numerator, natural log of n, I have 1 over n, and the derivative of n in the denominator is 1. So here we have applied L'Hopital's rule. So what we're left with is the limit as n approaches infinity of 1 over n, which is 0. Now we've got to be a little bit careful here. If we look at the terms that we were listing above for the sequence, it doesn't seem like they're approaching 0, and they aren't. Let's not lose track of what we found. Remember, what we just found was the value of the natural log of L. And L is the limiting value that we needed to find. So we still need to solve for L. So what we found so far is that the natural log of L is equal to 0. So to get the limiting value L, we would have to exponentiate both sides. We would have e to the 0 power, which is 1. So here, the limit of the general term of this sequence is equal to 1, so we would say that our sequence converges to 1. So in this first part of the section 5.1 material, we've introduced an infinite sequence and seen a couple of examples where we need to find an expression for the nth term of a sequence, or if we're given the nth term, we can determine if that sequence is converging or diverging. So in the next part of the section 5.1 material,